I'm Juxi Leitner. I'm a postdoc at the Australian Centre for Robotic Vision. And if you have the next 20, 25 minutes of time, definitely listen to me talking about how robots need to grasp the world. So I have a presentation. I hope to have some interesting questions at the end too. Quickly see if it actually works. It should work in about a second. So yeah, as I mentioned, my name is Juxi Leitner. I'm a postdoc at the Australian Centre for Robotic Vision. That's a national research initiative here in Australia, looking at how we can combine robotic systems with vision, especially visual feedback from camera systems. This is a national research initiative that actually involves multiple universities. I'm based at the Queensland University of Technology here in Brisbane. And what you can see there in the background is actually one of our robots. And that robot actually won the Amazon Robotics Challenge last year. And in the next 20 minutes, I'm going to talk about why I personally and a lot of other people believe that robots need to understand the world and need to grasp the world. So this is actually a pretty cool video of a robotic system. So what you see there, this is actually Tesla's factory. On the factory floor, there's lots of robotic arms. There's lots of robots that do a lot of things, and they pick up objects and they perform certain tasks with those objects. So we can do that, and we've been doing that for a couple of decades, actually. We can build robotic systems that know exactly where to pick up a car, how to lift a car, how to put it together, even like cell phones and something like this. So we're really good at that. But that's not what we really want. What we really would like to do is something like this. So this is WALL-E. I hope everybody has seen WALL-E. If you haven't seen WALL-E yet, go and do it now. It's a really cool movie about robotic systems. And what you can see in that movie is actually a robot that reasons about the world. It picks up lots of random stuff. It has a bit of curiosity, which is quite interesting. And if there's some questions about that, we can discuss this later on. But it basically needs to understand which part of the world is rubbish and which part of the world is not rubbish. And it's all big cluttered environment where you don't really know which part is what. And then actually pick up the right things and compress them to clean Earth so we can actually live on it. So we here at QUT are kind of inspired by that, and we want to build robotic systems that actually go out into the real world. So that's robotic systems that can interact with a lot of noise, a lot of data that it hasn't seen before. On a factory floor, we build a robotic system around the parameters that we know. So we know that the robot will have to pick up part of a car from this position and place it there. In fact, we are so good with that that we don't want any human anywhere close to them. The things that we're interested here in Brisbane is actually a variety of robotic systems. And this is some of the pictures of robotic systems that we're using. In the middle, there's a Baxter, there's a Now robot on the bottom. On the bottom left and right, that's actually robotic systems that were built here at QUT. The point is, we're trying to take these robotic systems out into what we call the real world, out of the lab, out of the factory setting, out of something where we have a predefined environment around things. And one of the crucial parts for doing that is to perceive the world. We need to understand what we see. We need to understand the environment that we're in. Again, in a factory floor, we don't care. We know exactly where things are coming from, where we need to stick them to, and we can basically do that blind. As a robot, I pick up a piece coming at a specific location at a specific time, and I expect it to be there. If I now actually build a robotic system that wants to go into my apartment or one of these apartments that you can see here, you can't really do that because every apartment is different. We can guess that the middle part is probably a bedroom and the lower one is a meeting room. But this is not something that's very easily encoded. It doesn't say like if there is this in that, it makes it a specific room. But even so, a robotic system needs to understand that. And so what you can see there in the middle, this is something what comes out of a depth camera. So this is a camera that actually measures the distances of every pixel and gives you information about this. For those that have an Xbox or something similar at home, your Kinect style camera actually provides you information like this. So a lot of roboticists use a Kinect camera and actually put it on your robotic system these days. And you get something like this in the middle. And that in the middle there is really the readout, where blue is something close to the camera and red is something far away from the camera. For humans to look at it, we still have a basic understanding of what's going on. For a robot, we're trying to get them to a basic understanding. And what we want to have is actually the last column. And the last column shows you what we call a semantic segmentation. It basically tells you all these pixels belong to the same object. For example, the bed or the table or the chairs. They all have the same color, meaning they all belong to the same thing. That actually turns out to be a really hard problem because every bed is different, every chair is different, every room is different. But we need to reason about these things to actually go out and interact with stuff that is not predefined. So how do we do that? Well, we have a Center for Robotic Vision, and we are interested in vision. Clearly, that means we want to put a camera on something. But cameras is not just because we really find it very interesting for us, but cameras actually exist all over the place. There's about 10 different eye designs. So not just the eyes that we have, there's basically all different. And when I say eye designs, it's just a sensor that measures light. And about 96% of all animals have eyes. Just a few of the animals that live at the very bottom of the sea or in very dark places all the time do not have them. So there's a big reason why these systems exist. And after the Cambrian explosion, you can clearly see that there's a lot of different designs out there. So a perceptive system that actually allows you to get a lot of information from the world is something that's very, very interesting and has been redesigned about 10 times. So that gives us a bit of an insight of like, this is very important, especially if you try to interact with a highly dynamic, changing environment like we do on every day. So we had a center funded about 3.5 years ago by now, that is trying to solve this problem. How do I actually get a robotic system to see, to understand the world around it, and to grasp literally that this pixel and that pixel belong to something specific? Actually, it takes a lot of effort and a lot of time, a lot of people to do that. And so we have about 5, 6 different research streams that we're working on between the 4 universities and about 100 people working on these. That's all the way from technology development to creating new sensors, to machine learning, to acting, and eventually to understand. So eventually the goal is we would like to understand the robot to the environment that you're in and that you work in. The most interesting thing for me is the acting part. So I'm leading one of the projects here called on manipulation and vision, which is in the green acting box. And it's basically, if you think about WALL-E, it's a robot that needs to pick up things. So how do you actually pick up things? Well, there's actually a lot of different problems that play into. One is clearly a hand. What you can see here, this is a European research project that started about almost 10 years ago by now. It's called the iCub humanoid robot, built in Genova in Italy. And what you can see here, this is actually a human-esque, it's not fully human, but a human-inspired hand. What you can see, there's 5 digits. Each digit has a lot of motors to actually control them. What you see in the back there of the hand, that's basically like all the control boards, the interaction, the parts that make the robot do stuff. You can see on the bottom there also lots of cabling going through, and actually like the wrist part is actually a very interesting problem for a robotic system to design, because all the motors for the fingers and the hand actually sit in the lower arm. And so all the cables have to route basically through a single point, which is an engineering challenge. The iCub solves that, and it's a really sort of immense effort on the engineering side to build a robotic system that can do these things. And this robot actually moves around. This robot can pick up stuff, but it's a very, very complicated problem, a very, very complicated robotic system to try to do that. So one thing clearly there is like, what sort of hand do I actually have to pick up things? This is a different robot called Baxter. It's a human-safe robot. If you're interested, ask some questions later and I can explain what that actually means. But what you can see, this robot doesn't have a hand. It basically has 2 pinch grasp elements. And that's basically 2 fingers, and you can only move parallel, and you can basically just pinch an object. Turns out that's good enough to pick certain things. In this case, you can see Baxter trying to pick, this is fake capsicum or red pepper from a fake bush. But actually, we have an agricultural robotics project here at QUT where we're trying to actually harvest these fruits in the real world from a real bush. So this is something where it becomes really interesting to see what do you need to actually pick up an object. So in this case, 2 fingers are good enough. So what is actually the right way of doing that? And so there's no clear answer to that. One of the really interesting things is that Amazon has the same problem. So Amazon sells a lot of stuff, but they can't really pick up these things. So there's still humans that actually pick up all the stuff that eventually you get in your cardboard box. So what Amazon did is like, how can we get researchers and lots of people excited about this problem so they solve the problem for us? And so what Amazon did is they ran challenges. So for the last 3 years, they have run the Amazon Picking and now the Amazon Robotics Challenge. What is the Amazon Robotics Challenge? It basically is, as I mentioned before, the challenge of trying to pick up an object from a shelf and place it in a cardboard box. Sounds really easy. I'll tell you actually why it's a bit harder later on. But so why is that the only problem that Amazon sort of still has? Amazon is actually one of the world's largest operator of robotic systems. So if you look into an Amazon fulfillment center, which is their fancy name for a warehouse, you see those orange robots that actually move around and shift these shelves around. Notice there's no humans in the back end. In the front end, you actually have a human, and you can see the lady actually waiting for a shelf to arrive, looking at her iPad screen, seeing there's this object that I need to put into the order box, pick it out, check if it's the right object, and then stick it in a cardboard box. Right, so Amazon has the problem that all the back side of their warehouses are fully automated, and the only sort of crucial part that's not yet automated is that part that you see right here. And why is that a problem for them? Amazon is still growing so fast that you cannot actually hire enough people to solve this problem. So Amazon has the problem that they don't get enough people to actually solve this problem, but they have enough people that want to order things that it will appear in the next 24 hours on the door frame. So Amazon wants to solve this problem. And so what Amazon said is, like, can we find a robotic system that actually is allowing us to look into like the shelf and pick up a certain amount of object? So we said, that's a really cool challenge. I can use cameras and vision and actually pick these things up. So we entered with Cartman, the Cartesian manipulator, last year. And as the name suggests, it's actually more of a Cartesian system than a robotic arm system. And you can see that here in action, or actually in a sketch. The action will come in a second. It's about a 1 by 1.5 by 1.5 meter cube. What the robot actually does, and that's on the left-hand side, what you can see here, there's red boxes on the bottom, and that's actually Amazon, what they call a tote. This is where, for example, their returns go in, or when they get shifted from the shelf to another shelf. In this tote, there's a certain amount of objects, and these objects need to go into like a different setting. In this setting on the left, it just means it needs to go into the red boxes on the left. In another setting, you actually need to actually put it in a cardboard box. So the challenge is, how can I, from a mess of about 20 objects, pick up the right object that the user ordered and stick it in the right box? So what's happening is actually 3 orders that need to be fulfilled at the same time. You have 3 cardboard boxes, and you need to stick the right object into the right box. What we're using is a camera system, and the camera system tells us where these objects are and what specific object we're actually looking at. So one of the things that we need to then do is actually pick those things up. And that's where the second part of grasping the world actually comes into play. The first thing is to understand where things are. The second one is actually to physically pick up the objects. So during the challenge, which was held in Japan this year, we, together with 15 other teams, tried to solve this problem on the fly. So this is a fully autonomous system that you can see here, and that's why you see the kind of bored student there in the back waiting for it to do something. And what you can see is that there's a big box of random stuff, and a specific object needed to be put from one box into another one, in this case, a book. What you can see here is one modality that actually allows us to pick those things up. And that's not a hand, that's just a suction cup. Turns out suction cup works for a lot of objects, and we've been using it for the last 3-4 decades in industrial robotic application. So it's a very good, very robust way of picking things up, especially if they're covered in like packaging or if they're box sized. Unfortunately, not everything is in a box, and not everything is covered in like cling wrap. So how do we solve problems where we don't have that? For example, the toilet brush there. So actually we designed a grasper similar to the pinch grasper that I mentioned before, that actually allows us to pick up an object like this and place it again in a different box. What you can actually see is that, let me just quickly go back to that one. What you can see is that it has 2 fingers, but they're moved by one single motor down here. Whoops. With a single motor down there. And basically it squeezes its finger together until it finds some resistance and stops. So this is, again, a very simple hand, but actually allows us to pick up things. The challenge for Cartman is to actually pick up the right objects at the right time with the right modality. And as it turns out, that's quite tricky. But to even make it more tricky, Amazon said, we have a different problem for you guys. We're going to change the objects on the day of the challenge to objects that you've never seen before. And that's tricky because what people have done in the previous years is that you use one of these modern deep learning techniques to learn a mapping from an image to an object. So you can say, this looks like a bottle of beer, a toilet brush, or whatever, and you learn that. It takes a long time to learn these things, and so you basically run your data sets for like weeks at a time to classify these objects. Amazon, on the other hand, has the problem that you get so many new objects on a daily basis that they need to be a lot quicker than that. So changed the rules of this year's challenge that you actually have to adapt to new objects. And that's by itself a quite difficult problem to solve. I don't think I can go into the details, but if you have some questions, let me know afterwards. So here's a rough overview of all the objects that we actually tried to pick or had to pick during the challenge. So the top 3 rows plus 1 is our training set. This is the objects that Amazon sent to us a couple of weeks, or actually a couple of months before the challenge itself. On the day of the challenge, we would get new objects. So we had to simulate new objects, and that's the bottom 2-ish rows that actually are random objects that we found somewhat in our lab or from last year's Amazon challenge, and said this is objects that we have not seen, that we haven't trained on, and we just still see how we can actually pick those up. What you can see is there's lots of different objects, from like a tissue box, a 3-pound dumbbell, a pair of scissors, all the way to a plastic wine glass and marbles, a bag of marbles. So there's a wide variety of things that you need to pick up, and there's a lot of different ways on how to solve that, but there's also a lot of shortcomings of current systems, especially around deformable objects and objects that move around. Taking a step back, now that we sort of can do that, and sort of the Amazon challenge has showed that we can pick a wide variety of objects, what can a robotic system now do with that? Once we actually allow to understand the world and physically grasp certain objects, once we actually get to this point that we can interact safely with the world, we can actually use this interaction to learn more about the world. Because I can poke things, because I can rotate things, I can open things, I'll learn more about how to perceive the world and how to interact with the world. And this is sort of the next step that a lot of people are trying to do. How can I get a robot, in this case the iCub humanoid robot again, to interact with an object in a way that actually allows it, in a playful, learning kind of way, to learn things about the world? And this is sort of the tying it back to WALL-E. This is sort of the curiosity aspect, bringing it back to how can I use robotic system to learn more about the world? So how do we go about this? Actually, to solve the grasping problem, we need a lot of different things. One of the most important things that a lot of people are thinking of right now is how can we compare different approaches? As you've seen, there's lots of different hands, there's lots of different grippers, lots of different robotic systems, and it's not that easy to compare from one hand to another hand. So we need some benchmarking and testing. We need to get inspiration from biology and neuroscience. We need to understand how we do things, how certain animals do things, and we need to find a way so we can actually start with a system, but then slowly learn and increase our intelligence, increase our capabilities of handling these things. On the other hand, we still need better materials. Like most of these hands are very stiff and they're not really flexible. They're not deformable enough like our hand. If you press your hand against the surface of a table or so, you actually see that most of your hand surface is deforming. And that's actually really helpful when you try to pick up things. We don't have the equivalent for a robotic system yet. And eventually you want to learn these things in a large scale with a lot of inputs and a lot of data. So we need some high performance computing, better graphics card, and HPC services like cloud computing. Thanks for that. This was sort of the 20 minutes overview of like why I believe that we need robotic systems that can grasp the world. If you have more questions, shoot now, or try to reach me at my email address and my webpage or via Twitter later on. Thanks for that. And I'm here for questions.
Yes, me too. So we have on it. I just saw it showed in the stream. What do you think about Amazon's plans to have a home robot?
Yeah, that's very new news. That's like within the last 24 hours, basically. So I think
you see our participants. Sorry, Juxi, our participants are up to date. Obviously, sorry.
That's perfect. I'm happy to talk about it. No, I think that's sort of one of the next challenges that we see as roboticists. We talk about unstructured environment as a scientific term for these things. A factory floor is a very structured environment. Things happen at a very specific time, at a very specific location, and we can repeatedly do things there. Sort of the very other end of the spectrum is an apartment. My house is a total mess. I leave, shirt here and socks there, and then my Roomba tries to run around and it gets stuck in cables. So it's a very unstructured environment because it keeps changing. And a lot of things keep changing. So it's sort of a natural progression to go towards more and more unstructured environment with the lead up to eventually solve the domestic robotic settings. For Amazon, I think there's also another thing at play. Amazon wants to eventually own sort of the whole logistics pipeline. If they have a robot at home, you don't have to be at home when there's actually a parcel delivered to you. And you basically have a robot that picks it up for you and leaves it there for you. And for Amazon, that just makes it even easier to deliver to you. On the other hand, you can test technologies like Amazon's Alexa, it's running on the Echo, to do human-robot interaction, to do natural language processing. I think they first start with something that's a lot more like a self-driving car. It just will drive around and try to avoid all these cables and socks lying around. But eventually, I think they'll try to solve the bigger problem of like, how do I deal with a very unstructured environment?
Absolutely. And by the way, just a side note, Westworld just started the second series, and this is a little bit a good connection as well. Imagine then you have someone opening the door and yeah. Okay. Then the next one, I think you answered it already. Carlo, he wants to know in what sectors do you see the most potential? I feel, or as you presented, I think in the retail sector or obviously, or what other sectors do you see like the benefits?
Yeah, so I think there's certain areas where we have now research and technology that can solve business cases and solve problems that actually have business value. Similar to like 10, 20 years ago, we could design a whole factory floor, which is perfectly fine for like a long-term investment and for processes that run for a long time. I think now with having robots that are a bit more robust to change, and that's a bit more, that's not totally robust to change, we can solve certain problems that, for example, SME manufacturing has, that retail has, that logistics have, where we need to pick up certain things that have more or less the same things, but they might be, for example, slightly different sizes. They might have slight different other material properties. For example, think of agriculture, picking fruit. Every fruit is more or less the same, but there's still slight differences between them. And dealing with that uncertainty, with that change, I think is something where we started to get good research output. And I think with some engineering, those will be the first ones that we can apply robotic systems to. I think eventually there will be a lot more robotic application areas. And that's the domestic setting that Amazon, Google, OpenAI, and so forth are aiming for. But this is still probably like a decade out.
Okay, thank you. And then we have more like a technical question from Vikram. For the Amazon challenge, did you use an algorithm to train your robot not to recognize objects, but to classify which type of arm to use?
That's a very good question. In this challenge, like the one that happened 2017, we used an algorithm to classify objects. So basically that's the semantic segmentation. It tells per pixel which object it thinks it is. It turns out by having only a very limited time to train, we're not really that good at it. So we need some fail-safe ways of dealing with that. And that's why we have a secondary cameras. That's why we have scales underneath the robotic systems. So we can fuse this information together to actually know that this is the right object. When it comes to picking up, we do have a heuristic approach that actually tells the system, for these objects, use the suction cup. For that object, use the gripper. Eventually, it has to fall back to try the other one. So basically, again, it's about the certainty and the fallback principles. But in this case, this was not learned. This is a very interesting question, and we're definitely interested in doing that. And we're having studies on how humans pick up objects that we hopefully can transfer to make the choice of this class of objects. They're all sort of like bottles or something like this. So they all have a similar graph. So you should pick them up with the same type of thing. Versus this is like sort of a phone. This is a box thing. I can definitely suck with my suction cup on one side of that thing. Right, so we're trying to learn these things, but for the Amazon challenge, there was a very pre-coded step-by-step thing of choosing the arm, the modality. Where to choose was basically based on a classification algorithm.
Okay, and I think we have then lastly a comment from Angelica, quite interesting. Thanks for your presentation, Juxi. Yes, definitely. Thanks for your presentation and for your time and for being with us. So now we are going to change now to the last session, and yes, then switch now to session 3, if you're joining us online or as well streaming on the meetup. Session 3 now with Gabi, so we will be live again like in 2-3 minutes time. And yeah, wishing you a great evening in Brisbane, and thanks again for hosting and being with us, and talk to you soon, and looking forward what comes next.
Thank you. Thanks for having us. See ya.
Absolutely. Bye.